So friends, welcome to this class of plate tectonics, and today we are going to discuss about the Indian seismicity. What does it mean to you? So India, we know it is a robust lithospheric system which is intruding into the Eurasian system, and this collision started around 55 MA, and the western part it is somehow older and the eastern part somehow it is younger. And most of this earthquake in India, if you see this earthquake distribution, most of them they are lying at the boundary of this Indian subcontinent, and very few they are inside, and they can be termed as the intraplate earthquakes like the Bhuj earthquake. However, some of these earthquakes here and here particularly, this is following in the Narmada Son graben or the Sonata graben, and here this Delhi Aravalli range, some of these earthquakes are following. So 95 or 99% of this earthquake they are following this plate boundary. So that is why seismicity in India are mostly by its plate tectonic setting and less are intraplate origin. So seismicity it is the plate tectonics reflection, and Indian subcontinent particularly the seismicity is totally you can say it is governed by the plate tectonics. And the Indian subcontinent is highly vulnerable to devastating earthquakes, and mainly because of this collisional tectonics. We have different historical earthquakes like 1905 earthquake, 1934 Bihar Nepal earthquake, 1905 Kangra earthquake, and 2001 Bhuj earthquake. So there are number of earthquakes, they are most devastating, and that earthquakes are nothing due to this interaction of these plates which are this India and Eurasian are going for the last 55 MA or so. And we know this convergence between these two plates that gave rise the Himalayan mountain system. We have discussed it many times during this collisional system, and we need not to discuss further it here. However, if you see about 59% of this land area of India is liable to seismic hazard damage, and this is the distribution of the different seismic zones. This India is divided into 4 seismic zones like 2, 3, 4 and 5, and different color index as given here. If you see this zone V, it is very high risk zone, area liable to shaking intensity 9 and above, and it is the zone 4 high risk zone, and zone 3 it is moderate risk zone, and zone 2 is low risk zone. So that means the whole Indian system 59% or around 60% of this Indian subcontinent land mass it is under seismic hazard. So let us talk further what exactly the origin of seismicity and why there are some uneven distribution and which area is seismically more active and how we determine it. So India has a varying degree of seismicity or regions ranging from the stable continental region, that is some part of are stable and with strong, that means greater than 6 magnitude earthquake in the Himalayas and northeast India, and Indo-Burmese Indian Ocean region it is characterized by magnitude more than 7, and this great earthquake more than 8 and 9, or this mega earthquake you can say it is more than 9, that is at the plate boundary zone particularly. And 4 zones that we have already discussed: zone 2 seismically less active, 3 moderately active, and 4 highly active, and zone 5 it represents the highest seismicity in the Indian subcontinent. And not only this, landward part, if you see this Andaman Islands, that is also coming under zone 5, because that is the plate which is the Indian plate which is subducting under the Burmese arc. The major earthquakes that occur along this Himalayan plate boundary, and this National Center for Seismology in India, it is the custodian for the seismological data, and you can get this information from this website. All these earthquake record of different magnitude, different place, that date, that can be found from this website, and you can take it and you can model for this future prediction of these earthquakes. And you see, these are this earthquake distribution of this Indian subcontinent and around, and particularly the Himalayan region, it is concentrating at this part. Now, the surface velocity field and seismicity of the Indian subcontinent. So, now the question arises how to measure it. We have to talk about the surface velocity field. That means the Indian subcontinent, it is moving. Now, how to determine whether it is moving? And this is the velocity measurement. Nowadays, the researchers, they are using GPS systems or GNSS systems to calculate the velocity field at different segments of this earth crust. But this velocity field, though we are measuring nowadays, it is going on for the last 50 ma or so. And due to this movement and continued convergence, that these earthquakes are occurring, and different time scales of the geological past that has recorded different rate of movement. In the last class, we are talking about the Indian plate movement was different at this different geological time scale, and those movement at different rate, that was also responsible for different magnitude earthquakes or different degree of deformation at spatially different segments of this Himalayan system. So, global positioning system or GPS measurement shows that the India plate is moving northeast at a rate of 35 to 38 millimeter per annum. So, now the question arises, what this around 4 centimeter per year movement, it will change the seismicity? Yes, it can. So, this is the superficial movement, and this 4 or this 3.5 or 4 centimeter per annum, it will affect largely into the rock structure and at the subsurface. And finally, this stress which is built up during this movement, it is either absorbed by these rocks and it is deformed, or it can be reflected in terms of their slips, their movements. And the geodetic data suggests that the deformation within the Tibetan plateau and its margins absorb more than 90% of this relative motion. Relative motion we have already discussed at the initial part of this class, and more the 19% or more relative movement, it is absorbed by the southern end of this Tibetan plateau, southern margin of the Tibetan plateau between India and Eurasian plate, with most centered on this 50-kilometer wide region of the southern Tibet. So, most of this relative movement, it is observed here. So, most of the relative movement is observed here. So, deformation is more intense, and this movement around 4 centimeter per year, it creates internal shortening of this plateau, which is account for more than 1/3 of this total convergence. And south of this Kunnul fault, if you see this geological map, in the south of this Kunnul fault, here the surface velocity field shows that the Tibetan plateau is extruding eastward relative to both the Indian and Asian plate. Here you see most of the strike slip fault, and it the sinistral strike slip faults are there. So, once the sinistral strike slip fault is there, that can be well reflected here at the GPS movement. This is the southern part of this Himalaya, you see this GPS movement is towards northeast. However, if you are reaching the Tibetan plateau at the southern boundary, this movement is just changing its direction, and you see this segment, its movement is either eastward or it is southeastward. So, that means through this faults, the strike slip fault, so this part of this continent, it is extruding from this active deformational front and it is going away from it, and this is called the lateral escape. So, this motion where the slices of this crust moves laterally out of the way and it is away from this colliding plate system, that is called lateral escape. And due to this lateral escape, number of crustal scale strike slip fault has been developed. And as a result, what is happening? Now, east of this plateau, North China and South China are moving to the east and southeast rate around 2 to 8 millimeter per annum to 6 to 11 millimeter per annum relative to the stable Eurasian plate. So, that means part of this system, it is extruding from this active deformation front or the collisional front. So, as a result, when there is movement, there is either extrusion or there is a deformation, there is a absorption of stress, there is a release of strain is there. So, that is why earthquake is very frequent along the Himalayan front and along the particularly the plate boundaries. So, this earthquake focal mechanism solutions that is compiled from 1976 to 2000 year, and it says that the thrust faulting occur along both the northern, southern and eastern margin of the Tibetan plateau. So, that is, if you see this distribution of this focal mechanism solution if you remember when we were talking about this earlier classes, we had a class on focal mechanism solution, how to do it. So, here you see the beach ball diagram distribution, it says most of these earthquakes they are of thrust fault origin. However, few of them there you say that is normal fault origin, and why it is normal fault origin that we have discussed in the earlier class also, because this compressional related extension. So, once we are compressing in this way, so we have to extend perpendicular to that, and extensional, that means it is providing or it is creating normal faults. So, that is why most of this fault, that means most of this earthquake distributed along this plate boundary, it is of thrust fault origin, and within the Himalayas thrust faulting is prevalent. So, we have prominent thrusts like the MBT, MCT, MFT. So, this most of these earthquakes in the Himalayas they are of thrust fault origin, and south of these Himalayas we have intraplate earthquakes. So, like this we have intraplate earthquakes, and some of these earthquakes they are related to this Sonada graben, that is Son Narmada Tapti graben, and some of this earthquake that is related to this extension of the Aravalli ridge, and some of them are purely intraplate earthquake like the Bhuj earthquake system. So, this south of this Himalayas intraplate earthquake and other geophysical evidence indicate this Indian plate is flexed and slides beneath the Himalayas, where it moves northward during the large earthquakes. So, that means we have this Indian plate which is subsiding down, it is at the below the Himalayan system. So, that is why we have different type, that means Indian plate which was just flexing down, and we have this Himalayas MBT, MFT. So, like that. So, this is the Indo-Gangetic plain. So, in this Indo-Gangetic plain, if you move, you will find the step like appearance of these faults. So, that this flexed Indian lithosphere it is going down on the Himalayan system. And north of this Himalayas, normal faulting and east-west extension is dominant. So, we are talking about this development of these rift basins, probably you can remember these rift basins are nothing the extensional basins, and this extension is nothing, it is the compressional related extension. So, due to this development of the rift basin, due to development from the normal faults, so if you are moving to the north of this Himalayas, that means you are going away from this compressional zone particularly. So, you are getting this normal faulting or extensional tectonic is dominating here, and strike slip fault that is dominant in the region around 1500 kilometer wide north of this Himalaya and extending eastward into Indochina. Here we have different strike slip faults are there, for which this part of this Tibetan system it is extruding from this active collisional front. So, that is why here this region it is mostly governed by the strike slip faulting, and active strike slip faulting occurs in the western Himalayan syntaxis also. So, here we have two in syntaxis. In the last class we are talking about, one is the eastern syntaxis and another is the western syntaxis. So, active strike slip faulting occur in the western Himalayan syntaxis as well as the eastern syntaxis in the Pakistan and Myanmar. So, here we have this eastern syntaxis and here we have western syntaxis. Both the syntaxis, they are recording this strike slip motion and this is the crustal scale strike slip faults are there. So, here in the geological map you can see in the western syntaxis, here this is the strike slip dominating and mostly if you see this is the sinistral strike slip fault. However, at the eastern syntaxis here at the Myanmar you can record here the dextral strike slip fault. And as the Himalayan system is bounded by these two strike slip fault and we have thrust in this side. So, that is why the south of the syntaxis in Pakistan, movement along the north strike slip fault or this north striking fault is dominantly sinistral and south of one in Myanmar is mostly dextral, that we have already discussed. So, these opposite sense of motion on either side of this India are compatible with the northward penetration of this Indian subcontinent into the Eurasian system, that we have already discussed when we are talking about the indentation experiment which was carried out earlier. We have a rigid system and we are putting or we are forcing to penetrate into this weak system, that is the Eurasian system. So, that is why this strike slip motion here and this strike slip motion here, for example, here this can be well explained in this the animated image. So, here this is the strike slip motion, you can see western syntaxis and at this side also you can see this side, this we have eastern syntaxis here. So, these two strike slip motion, that means making this Indian subcontinent isolate and it is penetrating into the Eurasian system. So, that means the Himalayan tectonics can be well explained with this combination of all these strike slip motion and their sense of displacement. So, these observations indicate that the convergence between India and Eurasia is accommodated by combination of shortening, east-west extension, strike slip faulting, lateral escape and clockwise rotation. And addition to that, uplift of the higher elevations of this Tibetan plateau by Miocene time indicates that the significant vertical uplift occurred after the India collided with Asia. So, that means not only the strike slip motion, not only this thrust motion, it is accommodating this movement of this Indian and Eurasian. So, there will be rise of this plateau, rise of this mountain system to accommodate this movement. So, currently these Himalayas are uplifted rapidly at a rate between 0.5 to 4 millimeter per annum and it experience very high rate of erosion along their southern flank. So, why it is at the southern flank, that we are talking about this climate and this plate tectonics, that is well explained there, but at currently this upliftment is between 0.5 to 4 millimeter per year and this upliftment is different at different segments of the Himalayas due to this locking system, due to this segmented system of the Himalayas. So, this is all about this plate motion and this earthquake on the seismicity around this Indian plate. So, thank you very much. We will meet in the next class.